Good afternoon and welcome. Welcome back. This is our 25th lecture, and let me just, as I usually do, give you an update on what we've been doing here. So, in the last lecture, we began by actually talking about, we began by formulating the problem of maximum likelihood code word decoding of a convolutional code as an MPF problem. And after that we said, okay, now we know how to formulate problems as MPF problems. So, how does one go about solving them? And we wish to solve the problem using this generalized distributive law approach. And the first step in actually applying the generalized distributive law is to actually construct something that is called a junction tree. So, the latter part of the lecture was devoted towards talking about junction trees. So, first we defined what a junction tree was, and then I showed you an example of a junction tree, and then the natural question is, well, how do you construct a junction tree? And towards that I actually stated a theorem, and we will go ahead and start our lecture by proving that. So, this will be our lecture 25. This will be our lecture 25, and what this lecture will be about, we will be talking about junction trees and message passing. So, examples of junction tree construction. So, as a quick recap of our last lecture, we began by completing our discussion on formulating the decoding of a convolutional code as an MPF problem. And after that I defined what it means to be a junction tree, we looked at an example, and then stated a theorem. And today our task is actually to prove the theorem. So, towards that let me do the following. Let me actually reproduce the theorem on the current lecture. Okay, so that didn't work too well. So I think I'm going to have to introduce a new page for that other copying that I'm attempting to do here. So let's paste that on this page. Okay. So here we go. So let me just, I'll just drag this down here. So if G is a graph whose nodes correspond to the local domains of an MPF problem and which is also a tree, then it must be that the edge weight must be less than or equal to the node weight of the graph minus n, where n is the number of variables, and that is also the size of the universal set. And the proof is actually quite simple. So the proof is let I believe so let's I guess we have to clarify what we mean by the node weight. The weight of a node associated to a local domain X Si is equal to the size of the set Si. On the other hand, the weight, the edge weight of an edge connecting nodes associated to X Si and X Sj is equal to the size of the intersection. And the node weight of a graph is equal to the sum of the node weight of the nodes in the graph and then the edge weight of the graph is equal to, in a similar way, it is equal to the sum of the edge weights of edges in the graph. All right. So, perhaps we should look at an example. So, I am going to use the same example we had last time. so in this graph you actually see that there are a total of 10 nodes, and these nodes over here have node weight 1 because they are associated with a single variable. These have node weight 3, right. So, from this it follows that the node weight of this graph, node weight of the graph is equal to 10. How about the edge weight? To look at the edge weight, what we have to do is we have to assign weights to the edges. So, when we are assigning a weight, let us say, to the edge connecting these two nodes, that weight is 1 because the size of the intersection of these two sets is 1. Similarly, it is 1 here. So, in fact, it turns out that for every edge here the intersection is actually equal to 1. So, let us just put that down. So, we will put down a weight of 1, 1, 1, 1, 1, 1, 1, 1 and 1. So, from this we get that the edge weight of the graph is equal to, let us add. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So, there are actually excuse me, there is an error here. The node weight is actually, there are 7 singleton nodes for a total of 7, but then there is 3, 3, 3. So, that should be 7 plus 3 times 3, that should have been 16. Sorry about that. The edge weight, on the other hand, we did compute correctly, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, the edge weight of the graph is actually equal to 9. Okay. And what our theorem actually said, the theorem that we are trying to actually prove now, it says that the edge weight of a graph associated to the local domain, given that it is a tree, must be less than or equal to the node weight minus the number of variables. So, in this particular case we see that the difference between the edge weight and the edge weight is less than or equal to 16 minus 7. So, since the number of variables is 7, the theorem holds in this case. So, thus the node weight, the edge weight, thus the edge weight, which is equal to 9, is less than or equal to the node weight minus 7, because this is 16 minus 7. So, we see that the theorem actually holds in this case, but we still have to prove it. Now, for the other part of the graph, so let us one other small piece of notation, let us actually call this entire graph G. Okay. So, this is a tree, and it is a tree where the vertices are in 1-to-1 correspondence with the local domains that arose from the MPF problem. Now, I would like to go back to our earlier lecture, and in which we actually talked about the projection of this graph. If you will recall, we said that here is a graph, and one way to test whether or not a graph is a junction tree, given that it is already a tree, is to actually take the graph and project it onto each of its individual variables. And if the graph that you get in that manner is in each case a tree, then you have that what you had originally is a junction tree. Okay. That was one of the two equivalent definitions of a junction tree. So, when we projected this graph, and here is the projection onto x1, you see these two nodes, and you see that this is a tree. Okay. So, in our notation, what we are going to do is we are going to call this, in retrospect, we are going to call this the graph G1. So, since I want to make use of this, let us again select the page and copy it onto our current lecture. Okay. And I am also going to use the next projection over here. So, let me select that as well. And copy that as well. Okay, good. So, we have both of these copied, and now I am going to term this, since this is the graph obtained by projecting onto x1, I am going to call this G1, and you will actually notice that the edge weight of G1 is equal to the node weight of G1 minus 1. Well, why is that? Well, first of all, I guess it is clear that by EW I mean edge weight. And similarly, that by NW I mean node weight. All right. And if you were given that this is a tree, then this is true, because in these projections every vertex is labeled with just a single variable, and the variable is common to all the vertices in the projection. So, the edge weight is also equal to 1. So, for example, so when you are actually computing this, all that you are doing is really this is saying the number of edges is equal to the number of nodes minus 1, but that always holds for a tree. Okay. So, just to point out that this is equivalent in these projection graphs to actually saying, so this is equivalent to saying that the number of edges in G1 is equal to the number of nodes in G1 minus 1, and this is true. This is true since G1 is a tree. All right. Now, let us look at a second projection here. So, this is the projection of the graph that we have over here onto the variable 4. So, when you project this onto 4, what you do is you retain only those vertices which contain 4, reject other vertices, and retain all edges that connect two vertices that contain 4. If you do that, you get the graph that I just showed you. And then even the other minor point is that even when we label with regard to labels, we drop all variables other than 4. So, again, once again you have the property that all the vertices have a single variable. So, their node weight is each equal to 1, and all the edge weights are actually equal to 1. Okay. So, once again you have in this case that the node weight of G4, the projection onto X4, is equal to 4, which is equal to the number of nodes in G4. The edge weight of G4 is equal to 3, is equal to the number of edges in G4. So, therefore, it is once again true that the edge weight of G4 is equal to the node weight of G4 minus 1. Okay. Right. So, now let us get back to our proof. So, our theorem and our goal is to actually show that if G is a graph whose nodes correspond to the local domains of an MPF problem, and given that the graph is also a tree, then it must be true that the edge weight of G, which is the sum of all the weights of all the edges, is less than or equal to the node weight of G minus n. And the proof is, so with this information, our proof goes as follows. We say that since see when G is a junction tree, we have, as we have just seen in the examples, that the edge weight of G is the sum of the edge weights of Gi, and since it is a junction tree, each of these projections is a tree. So, this is the sum I is equal to 1 to n node weight of Gi minus 1, which is by definition equal to the node weight. Let me put an intermediate step here. So, this is the sum I is equal to 1 to n of the node weight of Gi minus n which is equal to the node weight of G minus n. Okay. So, therefore, we have that the edge weight of G is equal to the node weight of G minus n, provided G is a junction tree. Now, so what happens? What would happen if, let us say, G were not a junction tree? What would happen is that if, for instance, this was not a junction tree, then what you would have is that when you project onto each of the variables, you would get a graph that is not a tree, in the sense that it would not be connected, and so it, in some sense you can view it as a union of trees, which in graph terminology is called a forest. Okay. So, perhaps I can do, let us see if I should let me right, I think that I will take this example, and yeah, perhaps it is best to illustrate with a second example. Okay. Let me delete all the material that I do not need. And let us say that in a certain instance, for example, we had that this thing over here was not a 4, but let us say that it was instead a 5. Okay. Supposing this was our graph in a certain instance, then when you project onto, let us say you project onto 4. So, in this case G4 would look like 4 corresponding to this node, then there would be a 4 which corresponds to this node here, and there would be a 4 that corresponds to this node over here. Okay. So, what you would have is not a tree, but in general a union of trees or a forest. Within each tree, it is actually true that the number of nodes exceeds the number of edges by 1, but when you add over all the trees, the deficit is no longer 1, but equal to the number of trees. Okay. So, for this reason we can say that when G is not a junction tree, then at least one of the Gi will fail to be a tree, will actually be a forest, will be the union of trees of greater than or equal to 2 trees instead. And hence, in this case what will happen is that the edge weight of this G I will be less than the node weight of G I minus 1. In other words, you will not, equality will not hold. Okay. So, you will have strict inequality. So, then when you, so as a result of this, when you go up here and try to do the same argument that you did for the case when G was a junction tree, and you sum over these edge weights, then you won't have equality here, you will have inequality here, which means that the edge weight is less than the node weight minus n. Okay. In this case, so let us give the equation that we had up earlier a number. So, let us call this 1, equation 1. And we would find, if we now proceeded to argue as when deriving 1, we would find that, or we would end up with, the edge weight of G being less than the node weight of G minus the number of variables. So, we would actually have this. Okay. The theorem now follows. And the reason the theorem follows is because we have already shown that the edge weight is equal to the node weight minus the number of variables when it is a junction tree, and if it is not a junction tree, you have a strict inequality. So, that proves that the largest value that the edge weight of G can possibly be is the node weight of G minus n, and when you achieve that equality, then what you have is a junction tree. Okay. So, the lesson to take away from this is that, well, it looks like you are trying to maximize the edge weight, right, and when you are constructing this graph, why do not we try to find a graph. So, you have a set of local domains, why do not we try to construct a graph out of it, which is a tree, and where the which connects all the nodes. So, it must be what is called a spanning tree, and it must have maximal edge weight. Okay. So, the upshot of all this is that this suggests that if the local domains can be organized into a junction tree, then that junction tree represents a maximal weight spanning tree for the collection of local domains. Now, in the computer science literature, there are two well known algorithms for constructing minimal weight spanning trees, but these are easily adapted to constructing maximal weight spanning trees. So, the algorithms that people commonly talk about are Prim's greedy algorithm as well as another second algorithm due to Kruskal. However, we will follow Prim's greedy algorithm, and I will not actually describe formally the algorithm, since I think it would consume perhaps more time than we have. What I will do, however, is just illustrate it in the case of some examples. Okay. A maximal weight spanning tree and we will abbreviate this by MST can be constructed using Prim's greedy algorithm which we will now illustrate. So, let us start with an algorithm which we came across some time back. And which I have reproduced here. So, this example taken from a lecture about 4 lectures ago. What we were interested in at that time was computing two different functions, okay. And you can think of this as an example of an MPF problem in the obvious way. One difference from perhaps some of the other examples we have looked at is that there are two objective functions in this case. Okay. So, these are our two objective functions. So, based on this we can make a list of our local domains. So, our local domains in this case are x, y, w, which is associated to local kernel f of x, y and w. Then you have x and z associated to g of x z, and then you have, looking at the objective functions, you have x, w and y. So, you have x w associated to, since this is an objective function, what we do in these cases is just assign a kind of a dummy local kernel, which is 1. And finally, we have just one more, which is we have the local domain y. Once again, since this arises from an objective function which is associated with the dummy local kernel 1. So, in this case we have these 4 local kernels, these 2 objective functions. The global kernel of course is the product of all of these, which is just the product of these 2. Okay. Now, we want to apply Prim's greedy algorithm to actually organize these local domains into a junction tree. Okay. So, there are 1, 2, 3, 4 local domains. So, we can pick any one of them and actually start the process. So, let us say that we pick x, z, just like that. So, we picked one of the local domains and we actually drew up a node. Now, our next task is actually to pick. Prim's greedy algorithm says, well, try to maximize your edge weight at every opportunity. Okay. So, that means that now you want to connect to one of these, you want to connect to 1, 2, 3, one of these nodes. You cannot repeat x, z of course. So, one of the 3 remaining nodes, while maximizing the edge weight. Well, the edge weight is the number of variables that lie in the intersection. So, you can actually connect to either this, because x, z and this have an intersection of 1, or you can connect to this, which is also an intersection of 1. But it turns out that so I will just make an side comment here, aside. It turns out that an edge connecting nodes x s I and x s j incurs a cost equal to q of s I plus q of s j minus q of s I intersect s j. So, let us call this equation 2. Now, I should point out that, so what I am actually saying is that given a bunch of local domains, you want to actually construct a local domain, and I have pointed out that if into a junction tree, and if a junction tree can be constructed, then that junction tree will correspond to a maximal weight spanning tree. So, let us instead apply an algorithm that gives you a maximal weight spanning tree, and we are going to use Prim's greedy algorithm. And so a greedy algorithm means that you look for instant gratification, that you try to actually maximize your current profit, you do not think long term. So, that means that whenever you have, given that you have an existing node, you are going to try to connect to another node associated with the maximum possible edge weight. So, that is our primary consideration, but sometimes, as in this particular case, you might be faced with 2 options, that is, given that we started out with x z and we want to apply the greedy algorithm, we could even either adjoin to x z either x y w or x w. Okay. And in such cases, then you can actually look a little beyond Prim's algorithm, that is, go above and beyond what you need to construct a junction tree and start thinking about this criterion. It turns out that the computational complexity of having in your graph 2 nodes that are like this, which are connected with an edge. In other words, if you have a graph like this, which has x s I, x s j, and these are connected by an edge, then it turns out that the cost of having, that there is an edge cost to having an edge like this in your graph, because after all you are computing, you are going to solve the MPF problem by computing the objective functions. So, that involves some computation complexity. So, the cost measured in number of operations, the operations being either multiplication or addition, it turns out that the cost in terms of the number of operations of having these 2 nodes connected in your graph is the size of the alphabet of the variables in Si taken together. So, for example, if Si consists of 2 variables, each of which is drawn from an alphabet of size q, then the size of the alphabet of the pair of variables together will be q times q squared. Okay. So, it is that sense that we mean this. So, the cost of having this particular segment of the graph is q of Si plus q of Sj minus q of the intersection, okay, size of the intersection. So, with that in mind, when you actually come down here and you say, aha, look, if I actually put this, I will incur a cost of x squared. Let us assume that all these variables are drawn. I think in our example all of them were drawn from an alphabet of size q. So, perhaps just to emphasize it, let me repeat that here. So, w, x, y, z all are drawn from A, and the size of A is equal to q. This was our setting. I guess I do not need the commas here. All right. So, given that and so I am going to then therefore choose to actually connect it to xw, because I know that the cost incurred will be less. So, I make this connection. Okay. So, there are a total of 4 local domains and I need to make this a spanning tree. So, I need to have a tree, I need it to run all through all the edges, and I want to maximize my edge weight. So, here my edge weight here turned out to be 1, and now I have y and I have x y w. So, Prim's algorithm says, well, I can either put x y I can either connect it to this or to this, but then if I connect x y w to this, I will maximize my edge weight, it will become 2, right. So, I am going to do that. So, Prim will say, in this case, let us actually put x y w down here, and now what I will actually have is an edge whose weight is 2. Okay. There is just one local domain left, which is y, and again it is clear that you must connect y here. Okay. So, you must connect y here. So, we do that, and the corresponding edge weight is 1. So, in this particular case, what we have is that and you can actually check, do a small side calculation to check that the node weight of our graph, the graph that we actually constructed in this way, is 8. That is the sum of the node weights of each of the nodes, and the edge weight is actually equal to 4, and the difference is equal to 4, which is equal to the number of variables. All right. So, that proves that this is a junction tree. Of course, it also proves that it is a maximal weight spanning tree, because the maximum possible value of the edge weight of this graph was the node weight minus the number of variables. The node weight is fixed because it is the sum of the sizes of these local domains. So, the only thing that was variable was the edge weight, and you made it as large as possible. So, this is the junction tree for this example. Thus, this is the junction tree for this example. Okay. Now, let us next look at a second example. So, let us go ahead and call this, we will also call this example 1. So, this is example 1. For example 2, let us go back to the Walsh transform computation. And which I guess perhaps I should see if I can quickly bring that down as well. Okay, so here is our example 2 now. So, perhaps I can actually delete this page here. So, this is our example 2, in which we have the Walsh transform, and you can actually see the local domains and local kernels very easily, but we will put them down again. So, the local domains, well actually we have computed them. So, perhaps we can put these down as well. Maybe not. Okay. So, I am going to repeat, never mind. So, I will repeat the local domains. So, the local domains are just from this computation, we have the local domain x1, x2, x3, we have x1, x4, x2, x5, x3, x6, and then x4, x5, x6. Okay. So, we have a total of 1, 2, 3, 4, 5. We have a total of 5 local domains. So, I will actually put these down. So, we have x1, x2, x3, and you have x1, x4, you have x2, x5, and you have x3, x6, and you have x4, x5, x6. The corresponding local kernels are although they are not very important in this case, but just to keep track of things, x1, x2, x3, minus 1 to the x1, x4, minus 1 to the x2, x5, minus 1 to the x3, x6, and f of x4, x5, x6. So, the reason I actually said that the local kernels are not important is because they do not come in to the picture until after you constructed the junction tree. Okay. So, when you are attempting to construct the junction tree, you are going to work only with the local domains. So, in this case we have 1, 2, 3, 4, 5, and we want to construct a local domain. So, let us adopt Prim's greedy algorithm. So, for that what I am actually going to do is I am going to try to construct it alongside these local domains. So, let us copy this page again. Okay, here we go. And now I am going to delete this which we do not need, and I will try to construct the graph on this side. So, supposing I started, it does not really matter. Prim's algorithm allows you to start from whichever node you pick. So, let us say I start with x1, x2, and x3. Okay. I start with, and let us put that down here. So, x1, x2, x3. So, that is my first node. And now, when I see that the maximal edge weight, if I append any of these, I cannot append this because the edge weight is 0. For any one of these, the edge weight is 1. So, I am just going to pick one of these at random. So, let us say that I put excuse me, let me put x1, x4 over here, and I connect this, and the edge weight happens to be 1 since the intersection is just 1. Now, again I look at this and I say, well, I now can connect, I have two choices here, and even if I were to apply this other criterion of actually minimizing the number of computations, q of Si plus Sj minus this, it is not going to resolve, it is not going to differentiate between these, because for example, I have a choice of appending either this or this to this. Now, if I append this to this, the edge weight is 2. If I append this to this, the edge weight is 1. If I append this, the edge weight will still be 1. The other computational angle will tell me that the computation involved in adding an edge between this and this is q cube plus q squared minus q. If I append this, it is q cube plus q squared minus q again. So, it really does not matter. So, for this reason I am just going to pick arbitrarily, and I am going to write x2, x5. I am going to put that here, and I am going to put edge weight of 1. Then I am going to go down here and put down x3, x6, and again the edge weight is 1, and that leaves me with just one node left, which is x4, x5, x6, and I can append this to any one of these. The Prim's greedy algorithm will in each case say, well, since your edge weight is going to be 1, no matter where you append this, I do not care. The computational complexity viewpoint says, well, I also do not care, because if I attach this to this, the complexity is q squared plus q cubed minus q. So, now at this point, if I apply Prim's algorithm, it does not make a difference, as I just pointed out how I connect this. So, I am just going to make an arbitrary decision. I am going to put down x4, x5, x6 over here. The intersection with this has edge weight 1. So, now in this graph, if I actually look at it, so let us call this graph as always G. I notice that for this particular graph, I have that the node weight of the graph, well, that is the sum of these node weights. So, that is 3, 5, 7, 9 and 12. So, this is equal to 12. The edge weight of the graph is equal to 4. You can see that just by counting the reds that you have 4. The difference is equal to 8, which is greater than the number of variables. So, what does that mean? So, that means that in this particular instance, we tried our best to construct a junction tree, and we know that if you were able to construct a junction tree, then that junction tree would be found by constructing a maximal weight spanning tree, and Prim's algorithm is guaranteed to give you a maximal weight spanning tree, and we did just that. So, we tried our best and we failed. So, what does that mean? Well, it means that you cannot construct a junction tree in the ordinary way through Prim's algorithm. There is another method, however, we may or may not have time to discuss that. So, the point here is that, so in this lecture, just to summarize quickly, what we were trying to do was show examples of how junction trees could be constructed. and in one case sometimes you can and sometimes you can't, and that is exactly what we illustrated. So, I think that is a good point to stop, and we will continue in the next lecture. So, thank you.